Good evening, all of you. How are you all? Some of you converted to offline. Yes, so happy to meet all of you again. And some of you are joined in offline. Yes, offline started in Hyderabad only. Yes. Okay. Hope almost most of the syllabus is completed for starting batches. Yes, 9:30. Actually, up to 5 I taken another class. That's why it is 5:30. Okay. 5 to 9 means up to 5 I am having another class. That's why 5:30 it is. Otherwise 5 only I take. Morning means because actually most of the people is attending in evening only, no? College goers and all. That's why it is evening only possible. Okay, anyhow. Yes, from basics. Basics means I think I not required. Already rotating machines completed. Okay. Basics again not required. So DC machines will take little less time. It won't like okay, no problem. It won't take much time compared to other parts of machines. DC is less time. Okay, and advantage of DC machines is in the less time means whatever it is, the weightage is same. So if you see in the last year, that is not last year, this year, GATE 2021, there is almost like no questions in synchronous, but DC machine is having good weightage. Okay, okay. For some of you it is not completed, no problem. Okay, no problem. For new batch induction transformer, both not completed. Okay, okay. Mess food. Okay. Then live class, no problem, no. Okay, no problem. Those who did not complete, because saying for those who joined very long back, the starting January, February at that time, for them almost completed. Okay, thank you, Mangesh. Some of your names looking getting so very long back we taken the transformers. That's why I forgot some names also. Okay, good. Dinesh, right? Okay, Mruganka, no problem. For new batch, only synchronous machine complete. Okay, okay. So I'm talking about those who joined January, February. For them, for new batch, it will come. The cycle will come again. So I don't know Ramakrishna because it is coming in the cycle. So you will get informed what is the next subject. Yes, anonymous certain. If you work for these few months, definitely because now hardly is October, November, December. Only 3 months for new topics. Only 3 months duration is there for new topics to be learned, and from January, that is only 1 month you should spend for only revision, and in the January month you should not learn any new topics. Okay, only for revision. At least in these 3 months, try to complete perfectly 4 to 5 subjects, minimum 5 subjects. Enough. Still, there is a chance to get good rank. Minimum 4 5 subjects in these 3 months. Target these 3 months. Prepare like anything, like you have never prepared in your life like that. So be spend these 3 months like that. Only 3 months. It will change your life. Okay. So transformers I only will take Shruti. New batch also, but not I don't know exact time when it is, but we'll take. Srinu almost volume is full only. Okay. Anonymous certainly. What is your name first? Thank you, Pratyush. Pratyush, yes, remembered. Anonymous attendee means what is your name? Okay. So DC machines nearly 8 to 10 days. That depends on in between. If 2 Sundays will come now, yearly it will complete. Okay. So nearly 35 to 40 hours required to complete this. Uh, yes, because so I have to take another batches also. That's why not possible to take complete machine at one place. Yes. So you should design or you should make your own notes, not short notes. Design your own notes directly first in the class because your notes only will help you during examination. Don't make short notes during the concept. Make your own complete notes. After that, in the revision time, you make short notes. But don't make now itself short notes. Make now full notes only. Don't depend only on this one. Okay. 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 See, in these 3 4 months, 3 months mainly, you try to concentrate those who are asking about which subjects is first maths, network theory, controls, and machines and measurements. At least these 5 subjects. Be perfect in these 5 subjects. And power system also some part will be easier theory subjects. So minimum this 5 first, after that go to power system. Like this 4 5 subjects be perfect. So in addition to that, even if you don't prepare properly, aptitude, some questions you can answer directly also. Okay, but minimum max networks, controls, machines, measurements. So little easier and scoring I'm saying. Okay, and easily you can score here itself nearly 40 to 50 marks. Perfectly prepare these 4 5 subjects perfectly, not like just preparing. Prepare perfectly 100 percentage. Okay, this 3 months. In the January month, completely revision of the same subjects. Don't go to new subjects in the Jan. So try to at least 3 months only. No, what is the problem? See, only 3 months. Struggle like anything in your life. Only 3 months. That will change your life. Thank you, Siva and all. Okay, but for those who complete, for which it is completed, I'm saying. Prerequisites, nothing is required for DC machines. You will understand clearly. Test series better to attempt from December. Signals is easy only, but problem is mathematical related. No, you should have all formulas and everything. Mostly formula related. That's why. So it is not better right now. So after completion of these subjects, then if you are interested, go to the subjects. Okay. Okay. Same to you, Baswan. Power electronics important only, but main problem of power electronics is it will take time to learn subject because there are many variations like rectifiers, only rectifiers if you take. Again in that half wave, full wave, semi converter, these are all formula related. No? That's why it will take time. So whenever it is required to prepare the subjects which will take less time to prepare, go through that first. And which is taking more time is then you have to keep it away for some time. Okay. Okay, okay, okay. So we will continue because so much time is there. We can talk in future. Okay. 5 subjects are max, networks, controls, machines, measurements. These 5 first. After that, power system. Yeah, I don't have an idea on IRMS when it is conducting. Thank you, Jan. Okay, okay, right. Measurements low weightage means not it is regularly. Sometimes you are getting some 2 to 4 marks, no, because compared to other subjects, measurements is easy subject. That's why I'm saying prepare that easily. Maybe it is syllabus wise little more, but you can easily prepare because only there are some standard questions based on PMMC or EMMC or MI instrument. Standard torque related questions, this type. That's why easily you can answer that questions. Okay. In machine subject, I don't say that this is more weightage. So whatever in machines, we have total 4 parts: DC machine, synchronous machine, transformers, and induction. So all 4 is having equal weightage. So I don't say that this is more important, this is less important. Written test, everything same, almost same weightage, written test. But if you attend interviews, their weightage is different. Then I can say that in interview point, these 3 are the more important interview way. But sometimes you will also face questions on DC regularly. Okay, but interview wise, DC machines less chance to ask. but written test wise, each and every topic is same weightage. Okay. 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 Let's see now. DC machines. So if you talk about gate examination, the weightage of, and for those who joined newly, so myself, Khadar Basha, okay, taking electrical machines, not required more than this. Introduction is not important. That's why I don't want to give more than this. Enough. Okay, gate. If you talk gate, in gate from DC machines, approximately we get 2 to 4 marks. 2 to 4 marks we can score from DC machines, like one mark question, 1 2 mark questions. Sometimes 2 1 mark questions, or sometimes 2 2 marks questions. But on an average, 2 to 4 marks we can score in gate examination regularly. Okay. Next, if you talk ESC, engineering services, particularly prelims examination, and we are having regularly questions approximately 3 to 5 questions. Regularly we are getting 3 to 5 questions. Okay, total electrical machines you are getting prelims questions is approximately 15 to 25. It is varying so much, sometimes 15, sometimes 20, sometimes like that 25, in this range. Total machines questions, prelims weightage is this, and in the mains examination we can expect 20 to 25 marks. 20 to 25 marks from DC machines. Okay. So advantage of DC machines is, compared to other machines, it will take less time and weightage is same. In less time, you are getting same percentage of marks like other machines. Okay. DC machines. Okay. Synchronous machines also easy one, not difficult. Synchronous advantage is uh, so to answer synchronous machines questions, particularly parallel operation, you should have good idea on the parallel operation topic first. Then if you able to understand question, you can solve the answer. If question is not understanding, then every question is difficult only. Okay, right. Next, let's see what is we are going to see in DC machines is this. So almost same syllabus for GATE and ESC, but for GATE from this year, that is with respect to GATE 2021, starting methods is removed in the syllabus. Starting methods is not there in the syllabus, and testing anyhow we don't have in GATE. Testing of DC machine we don't have in GATE syllabus. Okay, remaining all are there. Remaining all are there. But for engineering services, every line is important. All topics are there for engineering services. Okay, first we will see in the same sequence whatever we have here. Introduction of DC machine. So I will give some small basics to understand rotating machines and construction of DC machine. After that, types of DC machine, and overall in this the most important is this topic, armature reaction and commutation. The most important topic is this, armature reaction and commutation. Then we go to characteristics of DC machines, their generator characteristics, motor characteristics, both we will cover. After that, speed control. So if you ask which is the important topic for numericals, from where we are getting regularly questions, means I will say directly speed control of DC motors. Okay. Yes, starting methods and testing actually not there. Still, I will give the complete information of starting methods and testing of DC machines because it may help you in some other examination. Okay. Okay. Tomorrow, please note down the schedule for some batches. 2 to 5 p.m. 2 to 5 p.m. Linear algebra. This is for BTech completed batch students. This is for BTech completed batch students. Okay. Next, 5:30 to 8:30 p.m. DC machines. Yes, 5:30 to 9:30 p.m. It is not 8:30. 5:30 to 9:30 p.m. DC machines. This is for all. This is for BTech completed and college goer students batch. BTech completed batch and college goers. Okay. So please note down all of you this tomorrow schedule. For tomorrow timetable, 2 to 5 p.m. linear algebra for BTech completed students and 5:30 to 9:30 for all DC machines. Okay. Okay. Next. Okay. So this is we are going to see in the same sequence the complete DC machines. Let's see about introduction. In the introduction, you will see some basics regarding rotating machines. Now it will come. It will be uploaded. So you check by today's night. Today night. Okay. Okay. So update came now already. Yes. For those who completed, you no need to attend. For those who did not complete linear algebra, that people have to attend it. Okay. Next, let's see some basics of rotating machines. So I think some of you are good in basics of some rotating machines, but it is for all, for everyone should understand. So be patient for some time. Those who know very well about rotating machines basics. Okay. So first, in the rotating machines, suppose if you get any question in any interviews or anywhere, like if you attend particularly PSUs, no, PSUs interviews, technical interviews. So their common questions are this: what are the generators? How many types of generators? What are the difference in that generators? Only one question enough. And after that, the remaining questions will be based on your answers. Suppose how many generators we have? Mainly three types: DC generator, synchronous generator, induction generator. So try to tell one important difference in these three generators. One important difference. There are many differences. Constructionally, there are many differences. And operational wise, there is some differences among the three generators. Like these questions only you people need to face. Like in motors, we have many motors. DC, mainly if you talk DC motor, induction motor, synchronous motor. Tell one important differences between the three motors. like this type of questions. But still most of the electrical students are not having complete information about rotating machines, and they don't know what is the constructional difference between DC machine and synchronous machine, or induction machine and synchronous machine. So you should be very clear in all these fundamentals of rotating machines. See, only two rules will play, two rules will play major concepts totally in generators and motors. They are Fleming's right hand rule, Fleming's left hand rule. Okay, this is one statement, left hand rule and right hand rule. After that, right hand thumb rule. If you have very well how to apply these two rules, enough. Fleming's rules and right hand thumb rule. If you are very good at the two rules while applying in the machines, definitely you can play the rotating machines. Okay, so first write about generator. If you talk about generator, what is generator first? Generator, which converts the applied mechanical energy into electrical energy. The applied mechanical energy into electrical energy. Now, electrical energy means what you are taking from that. From the generator, what you are getting? Voltages. Voltage at some frequency. Okay, electrical energy means we are taking in terms of voltage and frequency. That voltage signal we are taking. Now, mainly we have three types of generators: DC generator, synchronous generator, and induction generator. So tell one important difference in these three generators. All are giving electrical energy, that is voltage frequency you are getting. Means if you talk particularly DC voltage, you will get some voltage with zero frequency. Synchronous generator, you will get voltage and frequency which are fixed or constant, but in induction generator also you will get voltage and frequency which are variable. So this is one important difference. All generators will not give same voltage and frequency. Okay, voltage magnitude may change, and frequency of DC generator totally zero, DC output. Synchronous generator constant frequency, induction generator variable frequency. Now what is the reason for this? DC generators always rotates at any speed n. Any speed you can rotate. Frequency zero only always. And voltage magnitude may change if you change the speed. But synchronous generator, what is the speed of synchronous generator? Synchronous speed. So there is one small funny question here, that is what is the speed of synchronous generators? What is the speed of synchronous generators? Synchronous speed. Yes, synchronous speed. That is only the answer. But here they asked in one of the interview, based on the name we are rotating at synchronous speed, or based on the rotation of the generator we given the name as synchronous machine. Which one is correct? First or second? First one is based on the synchronous machine. As it is named synchronous machine, we are rotating at synchronous speed. Second, based on our rotation, as we are rotating at synchronous speed, we given the name synchronous generator. First is right, second is right. Yes, second is right. Okay, enough. Second only right. Because some of the people think that synchronous machine means it rotates at synchronous speed. First of all, is the machine knows that I have to rotate at synchronous speed? No. Synchronous generators, suppose you rotate the generator, means that itself is rotating, or we are rotating? We are rotating with mechanical inputs or turbine inputs. Generator means we are rotating. So if you rotate it other than synchronous speed, the generator will rotate or not? It says that I don't rotate. No. Any speed it will rotate. But because of our responsibility or our requirement, as we need a constant voltage and frequency, we will rotate this generator only at one constant speed. That's why we call it a synchronous generator, because we are rotating at one speed called synchronous speed. That's why voltage is constant, frequency also constant. But induction generator, what is the speed of induction generator? We have to rotate the generator at a speed n greater than synchronous speed. Then only it behaves as induction generator. Induction motor behaves as induction generator if you rotate it greater than synchronous speed. So as there is no any condition, no, suppose synchronous speed 1500, rotate it 1600 or 1650 or 1700, any speed. If the speed is changing, what is the frequency and voltage of the generator also changes. That's why it is variable. Induction generator will never give constant voltage and frequency, but it will give when rotate n greater than ns constantly at 1600, then it will produce. But generally, where we prefer induction generators, at which power plants we prefer this? Wind power plants, or in some tidal plants also we use. Mostly in wind power plants, whatever we have, the turbines, they are wind turbines, or it based on completely wind. The speed of the turbine depends on wind force. Now there, if you consider one turbine also, what is the speed of the turbine? Tell me, is it always constant speed or variable speed? The speed of these turbines is not constant, they are continuously variable. They are variable, continuously speed will change because of wind force. Wind force is not always in same direction. So at one time wind force is in towards northeast or southwest or whatever it is. Whenever wind force is changing, its speed will change. Whenever the speed is changing, definitely the speed of the fan will change. Then internally the induction generator we are using, the speed of generator will change. If speed is changing, its voltage and frequency will change. Okay, that's why it is very difficult to maintain a constant speed in wind power plants. That's why the voltage and frequency of wind power plants is variable. Now tell one important question. Out of these three generators, in which generator we have more number of poles? Which generator is having more number of poles? Tell that. Synchronous DC induction. Which generator is always have more number of poles? Okay, enough. Okay, enough. Yes, most of you also given right. The answer is induction generator. See, generally in DC generator and synchronous generator, we prefer minimum poles are 2, like 4, 6, 8, 10. So in this range, the number of poles we design in DC generator and synchronous generator. But in induction generator, the poles will be in the range 18 poles, 20 poles, 22 poles, 24 poles, and so on. So this is the range of induction generator. Very more number of poles or more number of poles is preferred in induction generator. What is the reason for this? Yes, there is one good reason here. Observe. Why we preferred more poles in induction generator is to reduce the cost of power generation. To reduce cost of power generation. Suppose let us consider the number of poles in induction generator is 4. What is the synchronous speed? 120 F by P, that is 1500 RPM, synchronous speed. If you want to rotate as induction generator, what is the speed of induction generator must be? N greater than Ns. Okay, let for example N equal to 1600, greater than 1500 it is. Now, if you want to operate at 1600 RPM, so where we are using induction generator? In this turbine, that is wind turbines. Now, in the wind turbines, what is the speed of the turbine? Tell me. Is it high speed or low speed? The wind turbines speed is generally less, approximately 50 to 100 RPM, not more than that. 50 to 100 RPM, slowly they rotate. You can also count that in 1 minute how many rotations it is making. You can count easily. So very less speed will be there. Let us assume the speed of the wind turbines is 100. But how much speed you want? 1600. Then how to get 1600? Using gearbox. Using a gearbox. Gears. So gears is important. In mechanical engineering students, however transformer important for us, gears is important in mechanical engineering students. So what gear will do? Gears. What gear will do? So gear will increase the speed or decrease the speed. Step up or step down, just like transformer. However, transformer increasing the voltages or decreasing the voltages, step up and step down transformer. In the same way, gears, it can increase the speed of the wheel or decrease the speed of the wheel. Now that is gearbox. So we need to use a gearbox of ratio such that 100 RPM is converted into 1600 RPM. For that, 1:16 ratio gearbox required. 1 RPM is converted into 16 RPM, means the gearbox size is so much big. The size is so much increases. So whenever size increase, definitely its cost increase, its maintenance increase, overall cost of power generation increases. Overall cost of power generation increase. So is it economical of power generation? No. That's why we never preferred less number of poles. Now in place of that 4 pole, let us take 20 poles for example. 20 poles. Now what is the synchronous speed for this? 120 F by P, that is 300 RPM will come. 300 RPM. If synchronous speed is 300, we need to rotate greater than that. Now let us take example 400 RPM, greater than synchronous speed. But already turbine is rotating 100. So 100 RPM. Now we need to convert into 400 RPM. So it is easier or not? Yes. Then what is the gearbox ratio required? 1:4. Only 1:4 size gearbox required. 1 RPM converted to 4 RPM. So size reduces, cost reduce, maintenance reduce, overall power generation cost will reduce. So this is economical power generation. That's why in induction generators particularly, we prefer more number of poles when compared to DC generator and synchronous generator. Okay. So this is one important difference in generators between poles. Okay, next. One more. See, one more. Out of these three, what is the operating power factors of these generators? Tell me. Operating power factor. At which power factor DC generator operate? At which power factor induction generator and synchronous generator? Remember, DC generators always operates at UPF, unity power factor. That may be generator, that may be motor. It is always at UPF only. Next, synchronous generator. At which power factor it operates? It can operate at any power factor, like lagging power factor, leading power factor, UPF, unity power factor. Anywhere it can operate. So already you have seen this in synchronous machines. Armature reaction depends on loads. If load power factor change, reaction will change. Demagnetize, cross magnetize, or magnetize. Like that, it can operate at any power factor, just like transformer. Transformer also same, no? Any power factor we can operate. Anything we can connect to transformers. Synchronous generators also same. Next, induction generator. Tell at which power factor induction generator operates? It operates only at leading power factor. It operates only at leading power factor. ऐसा कुछ नहीं संचित. Why we mostly study about motors, not generators. वैसा कुछ नहीं. दो भी ऑलमोस्ट कंस्ट्रक्शन तो सेम है दोनों का, इसलिए ओके ओके राइट. Induction generator always operates at leading power factor. It always operates at leading power factor. Induction motor is lagging, but induction generator is leading. Why it is leading power factor? Tell me. Important question also it is. Induction generator always operates at lead. The reason is, if you remember synchronous generator concept in parallel operation, when we can say that synchronous generator operating at leading power factor in under excitation condition. Whenever synchronous generator is under excited, what is its power factor? Leading power factor. Its power factor is leading, and effect of armature reaction is magnetization. Now, in under excitation, what is the reactive power? Alternator is absorbing or delivering? The alternator absorbs reactive power. Under excitation, the alternator absorbs reactive power and delivers active power. Okay, I think all of you remembered this. Reactive power is absorbing, active power is delivering by generator. Induction generator also same. It absorbs reactive power and it delivers active power. Absorbs reactive power and delivers active power. Now, this case is similar to alternator operating at leading power factor or not? Yes. So, in the same way, we compare these two. Induction generator also absorbs reactive power, because what is the reactive power purpose? To maintain flux in a generator. We need to maintain a proper flux so that EMF will be constant. So, during that, it will absorb reactive power. So, required flux is produced by the reactive power. Due to that flux, EMF or voltages will maintain constant in the generator. That's why we consider induction generator always operates at lead. Okay, just by comparison of these two. Synchronous generator leading power factor is under excitation. Okay, synchronous motor it is. Synchronous motor under excitation is what? Lagging power factor. They are opposite exactly. Okay. So these are some important differences. Like this, there are many differences. If you go to constructional difference, what is the constructional difference between DC generator and synchronous generator? Both are almost same, but in DC generators, there is an additional device, commutator. If you remove that commutator in the same DC generator, that is a synchronous generator. You can make it is synchronous generator by rotating at one constant speed. Okay, and can we call induction generator as alternator? Tell me. This is also, I think, one of the prelims question it is. Can we call induction generator as alternator? Tell. Can we say induction generator as alternator? No. No, because alternator is a generator which produce an alternating voltage signal at constant frequency. That is important. Remember this, because some people will think that induction generator also giving alternating voltage signal, so it is also alternator. No. Alternator is a generator which produce a constant frequency signal. But induction generator cannot produce that because its speed is changing. Okay. Next. The basic for every generator is what? Faraday's law. So again, Faraday's law, write briefly once. Faraday's law. So what is simply Faraday's law? Whenever conductor cuts the flux or flux cuts the conductor, an EMF will induce in conductor. Write the statement. Whenever a conductor cuts the flux or flux cuts the conductor, an EMF will induce in the conductor. Like there is some other definition also. Whenever there is a change in flux linkages in a coil or conductor, there will be EMF, anything induced in the conductor. Okay. Now, if you place a conductor in a magnetic field, if you place a conductor in a magnetic field, an EMF will induce, but not directly. Due to some relative variation only, EMF will induce. So let's see what it is. Suppose there is a field here, magnetic field is there, north to south, flux is there. Now in that field, let us place one conductor or copper wire is placed. So when you place a copper wire, EMF will induce in the conductor? No, because there should be some relative variation. There are two variations we have. There are two variations. So for Faraday's law, we required conductor and we required flux and we required relative variation. So relative variation is one should vary, one should be stationary. Out of the two, then only EMF will come. Otherwise, if both are stationary, no EMF. If both are rotating, there is EMF, but there must be some variation between the two, that is two, conductor and flux. So there are two variations. One is relative space variation. Relative space variation. And second, relative time variation. Relative time variation. So I previously given in the transformers for previous batches. What is the space variation? What is the time variation? What is the space variation? In space variation, the flux is time invariant flux, that is DC flux. The flux is DC flux. So flux may be constant or flux may be alternating flux, anything. In relative space variation, we use the flux is DC flux. But in relative time variation, whatever the flux we are using, that is alternating flux, time variable flux. Whenever flux is variable, that variation we call time variation. Whenever flux is constant, that is we call simply relative space variation. See, in generators, DC generator or synchronous generator, anything, we are using this one only. So DC generator, synchronous generator. The variation is this, space variation. But where we have relative time variation? In transformers. In transformers, we have relative time variation. Relative time variation, because if you remember, what is the nature of flux passing in transformer core? Alternating, because supply is alternating, source current in winding also alternating, the flux produced is also alternating. That is relative time variation. And in the transformer core, windings are stationary, they never move. But even they are stationary, as flux is alternating flux in the core, some EMF will induce in that. Okay, that is relative time variation. But in space variation, observed whether it is DC generators or synchronous generators. Suppose already synchronous generators you have seen. So there, poles or field is in rotor field. By giving excitation to the field winding, the rotor is rotating at the same time, means poles are rotating or not? Yes, that is flux is rotating. That rotating flux will cut the conductors, three phases synchronously. Then we get a constant three-phase voltages. that is with 120-degree displacement, constant, that is constant means alternating only. The voltages we are getting with the same displacement continuously, because same constant speed we are rotating. Same magnitude of voltage in every phase, because every phase will have same number of turns, same voltage will be there, and same magnitude of flux is cut by every coil or every phase. That's why a three-phase signal we will achieve there. Same way in DC generators, we have DC excitation or flux is DC only. But what is the main difference in DC generator and synchronous generator is, in DC generator, the poles is in stator, opposite to synchronous generator. So where is the poles in synchronous generator? Rotor. That poles we are rotating at synchronous speed. But in DC generator, the poles will be in stator and armature winding will be in rotor. The armature winding in generators nothing but conductor. Conductor only we call armature. Armature. So in rotating machine, conductor and flux anywhere you can place. Anywhere. Place the conductor in stator, place the flux in rotor, or take opposite also. Anything if you take, you will get the EMF. But in DC generator, we should place armature in rotor only. That is, winding we should place in rotor only. Otherwise, you don't get DC. So we will see clearly in the simple loop generator how we are getting DC voltage using commutator. Without that commutator, there is no DC generator. See, simply you can call like this: DC generator is simply synchronous generator plus commutator. So in the same synchronous generator, add a commutator. Or what is synchronous generator? In DC generator, remove commutator. You will get synchronous generator. Remove commutator and in place of commutator, use slip rings. Slip rings. You will get AC voltage and frequency. If you want constant voltage and frequency, rotate at constant speed, called synchronous speed. See, first we complete this. So in order to satisfy Faraday's law, we required mainly three things. One is conductor, flux, third one relative space variation or relative time variation. But in the generators, we are using relative space variation, where flux is time invariant flux. Flux is time invariant. Okay, so anyhow, now EMF induced in the conductor. How to find the direction of EMF? How to find the direction of EMF or current in conductor? That is by using Fleming's right hand rule. That is by using Fleming's right hand rule. Now, I think most of you know about this. Now, my question is, Fleming's right hand rule statement and left hand rule statement, both rules are same or different? Statements of this same or different means whatever the fingers is there here in the right hand, middle finger, forefinger, thumb finger. Now, whatever is there in left hand rule, middle finger, forefinger, thumb finger. So these are same or different? Tell me that point. In the Fleming's right hand rule and left hand rule, both are same or different? Yes, some of you saying different, some of you same. Yes, the answer for this is both are same. Right hand rule, left hand rule, both are same. Both are same only. Okay, both are same. So I will show you how both are same in the both Fleming's right hand rule and left hand rule. So don't divide the subject like this. So most of the people think this is different, this is different. Maybe right hand, left hand, that is different only. But what I am asking is statement. The three finger statement of this and three fingers of this, both statements are same. Okay, then only it is easy. Otherwise, you have to remember this statement, you have to remember this statement. Both are same. What is the Fleming's right hand rule statement? If the three fingers of right hand are kept mutually perpendicular like this, see, thumb finger, forefinger or index finger, middle finger. Then what is the indication of index finger or forefinger? direction of flux. Forefinger indicates direction of flux. Thumb indicates motion of conductor, in which direction conductor is moving. Then middle finger will give the direction of EMF or current. Okay, so you should be very perfect by applying this statement in the figures. By applying this only, we have to mark current direction. Then only you can understand. So there is one important topic I said, armature reaction. Armature reaction. So very, very important. So there you will get so many important discussions, important points. That points are valid for every generator. For synchronous generator also, whatever the doubts you have still in your mind, every doubt I will clear in armature reaction topic. Okay, so maybe you people have some doubts in the hunting topic, hunting in synchronous generator. So what are the reasons for hunting? Sudden change in excitations, or sudden change in loads, or sudden change in turbine inputs. These are all reasons for hunting. Now, most of the people will get doubt that, sir, I am rotating at synchronous speed using mechanical turbines. Turbine, I am rotating. Then how speed of alternator will change? Just think this. We are rotating with a mechanical input at synchronous speed. Now, due to some load changes, how speed of alternator will change? Because turbine input same, then how it is changed? Yes, it will change. The speed of alternator or generator will change. That is not due to the effect of turbine input. That is due to effect of internal, that is load conditions or excitations and all. So how the speed is changing? So all these points I will show you in the armature reaction topic. Okay, wait up to that. And there are two more important points. That is, in a generator, first tell me in which one we have torque. Generator, motor, both. Where we have torque? Torque is present in which machine? Generator, motor, both. Answer this. Torque is present in which machine? Yes. Torque is present in both. Yes. Torque is present in both. Generator also there is torque. Motor also there is torque. Now in generator direction, what is the direction of torque? In generator, direction of torque is dash. Suppose if you rotate clockwise, the torque produced in generator will be anti-clockwise. Now the proof I will show you there. And motor, in motor direction of torque is, suppose torque is in anti-clockwise direction. In which direction motor rotates? Same anti-clockwise only. Motor always rotates due to torque. In whatever the direction torque is produced, same direction motor also rotates. So these 2 points proof also I will show you in armature reaction. Okay, so very important, armature reaction only. If you understand armature reaction of DC machine, and after that remaining all topics will be easier. Okay, so wait up to that. Now see here, the direction of EMF in conductor, EMF or current in the conductor can be found by Fleming's right hand rule. So write that statement. The direction of EMF or current, the direction of EMF or current can be found by using Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. So see the statement of this. So mostly everyone knows about this, but still just briefly I'm giving. Right side heading, Fleming's right hand rule. Now write the statement directly in the short way like this. If forefinger or index finger we call, if forefinger indicates direction of flux, and thumb finger indicates direction of motion of conductor, direction of motion of conductor. Then middle finger indicates direction of EMF or current, direction of EMF or current, direction of EMF or current. Okay, take the statement. Remember, forefinger is flux, thumb finger is motion, in which direction you are moving the conductor in the field, clockwise or anti-clockwise. And middle finger will give the direction of EMF or current. Let's see one question. Try to answer this question. The direction of current, the direction of current in the following figure is dash. The direction of current in the following figure is dash. So take the figure. See, this is conductor 1, 2, 3, 4. Now, based on the figure, at the instant of the figure shown, tell what is the direction of current in the conductors. Conductor 1, what is the current direction? 2, what is the current direction? 3 and 4. Current direction. How we indicate current direction generally? Cross. Cross means going inside the board or inside the paper. Dot means the current is coming outside the paper or outside the board. Okay. Now apply your Fleming's right hand rule here and try to tell what is the current directions in this. Oh, yes. Observe here. Okay, right. 1 cross 3 dot. Okay. Observe here. See, before finding current direction, what you have to do is mark the motion of conductor. Mark the motion, in which direction or motion it is moving. That is important for us. Observe here, rotation is given clockwise. Rotor is rotating clockwise. When rotor is rotating clockwise, the conductor 1 will move in which direction? Upward direction, because motion is like this. If it is rotating clockwise, 1 will move upward direction, and 2 will move in this direction, and 3 will move in this direction, and 4 will move in this direction. So whenever rotor is rotating like this, then motion of every conductor at that point we mark. And what is the field direction? North to south. This is the field direction. Now apply your Fleming's right hand rule. Forefinger is flux direction. Forefinger is flux direction. Thumb indicates motion of conductor. Now, wherever you want to find current direction, put your middle finger at that conductor. Suppose I need at 1. So at conductor 1 exactly, suppose it is a conductor 1. So place your middle finger there. And what is the thumb finger? Upward, because motion is upward direction. Forefinger is field direction. Then my middle finger, I'm getting middle finger is going inside the board. So at conductor 1, current is going inside. Middle finger going inside the board, that's why cross it is. Now at conductor 3, what is the direction of current? Forefinger, same direction. Now let's just move your thumb finger exactly down, because motion is downward direction. Then your middle finger will come outside the board or paper. Outside the board or paper means dot. Okay. In conductor 1, current is cross. In conductor 3, current is dot. Now in conductor 2 and 4, what is the current? 0. EMF or current is 0. The reason is at this position, the motion of conductor is parallel to flux direction. Flux line is moving in this direction. Conductor is moving exactly parallel to that, maybe in opposite direction or same direction, anything, same direction. Then there is no flux cutting action. So here conductor is not cutting any flux line. Then no EMF will come. Whenever conductor cuts the flux, then only there is EMF. Otherwise, no EMF here. That's why in conductor 2 and conductor 4, the EMF induced is 0. And the axis wherever EMF induced is 0. That is we called the axis wherever the EMF induced is 0. That is we call, what is that name? The axis wherever EMF is 0. This axis we call neutral axis. That is magnetic neutral axis, MNA. Okay. The axis wherever EMF induced is 0. That is called magnetic neutral axis, because magnetically there is no effect of north pole, no effect of south pole. That is a neutral point. That's why under north pole, observe what is the direction of current? Cross. So north pole effect. Under south pole, what is the direction of current in the third conductor? Dot. That is south pole effect. But at second conductor and fourth conductor, there is no effect of north pole, no effect of south pole. That's why EMF is 0. And that axis we call magnetic neutral axis. And the same axis we call Q axis here, because the axis passing through the main poles we call D axis, direct axis, also called polar axis. It is polar axis. And this axis we call Q axis, which is perpendicular to the D axis, and also called MNA here right now, because along this axis no EMF will be there. Okay, because along this axis the motion of conductor is parallel to flux line. The motion of conductor is parallel to flux line. That's why no flux cut by conductors, no EMF will be there. No EMF. Next, one more question. Why rotor is always circle in shape? Tell why, what is the need of circle? Tell me. If rotor is not circle, what is the problem? Yes, there is very big problem. If rotor is not circular shape, suppose take a square shape or take any other shape, it is not mechanically balanced. When you rotate this square shaped rotor or any other shape of rotor, it is not mechanically balanced. Because of this shape of rotor, your bearings will damage first. Bearings cannot withstand this unbalanced forces because it is not smooth surface, so it cannot rotate smoothly. So mechanically unbalanced it is. Only circular shape is mechanically balanced. That's why we preferred always circular shape. Okay. Yes, uniform flux distribution also possible. Yes, right. Okay, right. Right, one more question. So this is previous gate question only. Question. Write the question. A field is rotating around a stationary armature. A field is rotating around a stationary armature. A stationary armature having two coils. Having two coils as shown in figure. As shown in figure. At the instant shown, 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 Which of the following is correct? Which of the following statement is correct? Which of the following statement is correct? Check the figure. Sanjay, any doubt?
No, sir. No, sir.
Okay. What is the answer for this? Okay, right. Okay. Okay. Yes, most of you given right. The answer is option A. A is correct. So first of all, two options you can eliminate these two. C, D you can eliminate. Why? Because along at this instant, what is EMF along this axis? Zero. This is MNA here, magnetic neutral axis it is. So along this axis, EMF zero. So no EMF in C2. That is right. So no EMF in C2 is there are two options. Now we have to find dot in C1 or cross in C1. Which one is correct? For that, simply observe. But most of the people also may do mistake here. That is, flux direction is north to south. So mark the direction of flux. Now here armature is stationary. A field is rotating around a stationary armature having two coils. Means armature is stationary, a conductor is stationary, field is rotating. Generally, according to Fleming's right hand rule, Fleming's right hand rule is valid for rotating conductors or stationary conductors. Directly, it is valid for rotating conductors. Why? Because what is the thumb indicates in that motion of conductor. But here, conductor is not moving first. Then how can you apply thumb? So directly you should not consider motion of field here. Field poles are rotating like this clockwise. So you should not take that motion. Motion means motion of conductor, but not field motion. But in this question, field is rotating, conductor is stationary. So whenever this type of conditions arrived, then one assumption we have to take here, that is field is rotating clockwise. Now rotate the rotor or conductor in the opposite direction of field. Just assume that it is rotating counterclockwise direction, opposite to field direction. Just assume like that. Assume the direction of motion of conductor opposite to field. Now apply the Fleming's right hand rule. Now if rotor is rotating anti-clockwise direction, how C1 will move? C1 will move in upward direction or not? Yes. C2 will move in this direction. C1 dash will move in downward direction. C2 dash will move in this direction. Now C1 is upward. Apply your Fleming's right hand rule there. Flux is in this direction. Motion of conductor is upward direction. Now middle finger. Check your middle finger coming outside the board or outside the paper in your book. Then dot will be in C1 and cross will be in C1 dash. So dot in C1 is correct. Dot in C1 because motion of conductor is upward direction. Apply your Fleming's right hand rule here. Apply your Fleming's right hand rule. Okay. It is upward. Motion is upward because we need to consider direction of motion of conductor opposite to field. Field is clockwise. That's why we take an opposite direction. Okay. Make a note here. Make a note. Note. Whenever field is rotating, whenever field is rotating, then consider the motion of conductor. Whenever field is rotating, then consider the motion of conductor opposite to field direction. Then consider the motion of conductor opposite to field direction. And then apply the Fleming's right hand rule. And then apply the Fleming's right hand rule. And then apply the Fleming's right hand rule. Next, write in the note only another point. Next, another point. Second point. This is regarding voltage regulation in generators. So if you remembered voltage regulation of alternator. So voltage regulation is there in alternator, DC generator, and also transformers. So wherever voltage generated, there you will have voltage regulation topic. What is voltage regulation? That you know. Now voltage regulation is three types of positive regulation, negative regulation, zero regulation. Three types we have. Okay. Now in synchronous generator also most of the people have seen recently positive, negative, zero. Now how you are getting positive, negative, zero? For different loads. Different loads you are getting. Positive regulation you will get for lagging power factor loads. For UPF also positive you get, and for leading also you will get positive. And negative regulation is for only leading power factor, and zero regulation also only for leading power factor. Same for transformers also. Same as it is for transformers. But now in DC generators, the regulation we have voltage regulation. Again, here also we have positive regulation. Here also we have negative regulation. Here also we have zero regulation. But how it is possible? Tell me. How regulation is different types in DC generators? Because there is no loads now here. In DC generators, do you have these types of loads? These types of loads? No. DC generator always operates at UPF. And there is no other lagging load, leading load. We cannot connect because DC it is. Frequency zero. Inductive load, capacitive load not suitable for this. Then how regulation will change? Even there is no load power factors, how regulation of DC generators will change? Yes, it will change because it depends on type of generator, but not loads. Type, we have separately excited, shunt, series, compound, different types. Whenever type of generator will change, your regulation will change. So how it is changing, that we will see in the characteristics clearly. Okay, so remember this point. Voltage regulation of DC generator does not depends on load power factors, but it depends on type of generators, but not loads. Okay, write that point in your notes. The voltage regulation of DC generators depends on the type of generators, the type of DC generator, the type of DC generator, but not load power factor, but not load power factor. Okay, but not load power factor. Now, next point. Next point. Now, in a generator, we have torque. Not only motors, generators also there is a torque in generator. However, there is a torque in motor. Generator also there is a torque. Now, the torque direction in generator is always opposite direction of rotation. So, how this is? So, I will show you in the figure of armature reaction. Right now, I cannot because there is some proof required. Directly saying is different and showing the proof is different. So, write the point here. I will show the proof of this in the armature reaction topic. Okay. So, write that point. In a DC generator or in a generator, in a generator, in a generator, the electromagnetic torque developed, the electromagnetic torque developed, developed is always in opposite direction of rotation. Is always in opposite direction of rotation. In opposite direction of rotation. So how it is opposite? Okay, and all these points we will see there. Just remember here meanwhile. Next, fourth point. In a motor, the electromagnetic torque. Okay, first point again. In a generator, the electromagnetic torque developed is always in opposite direction of rotation. Next, in a motor, the electromagnetic torque developed is always in same direction of rotation. The electromagnetic torque developed is always in same direction of rotation. So this third point and fourth point, both I will show you the proof also. Okay, and what is the use of the torque also in the armature reaction topic. So that's why in armature reaction topic, in between, if anybody has any work and also, and try to attend on armature reaction must. Very, very important topic it is. Okay. So this is regarding generators. This is regarding generators. Next, let's see about motors. 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 Now, what is the motor function? Function of motor is what? It is a device which converts the applied electrical energy into mechanical energy. Into mechanical energy. Okay. The applied electrical energy is converted into mechanical energy. Now, mechanical energy means in the form of speed. Speed only we are collecting outside. So what you are taking in a motor? Speed only. Yes, speed from the shaft of the motor. Speed we are utilizing. Speed. So take a ceiling fan in your home. Ceiling fan. Now, what you are utilizing there? Speed you are utilizing. So you may rotate at low speed or you may rotate at high speed based on your requirement. That is speed control of motor using regulator. Now, in every motor, you don't get same speed. Suppose let us consider DC motor. DC motor. In DC motor, what is the speed you will get? N. Any speed you may get. N. No comparison. Only in AC machines we have comparison of synchronous speed, but no comparison in DC machines. Generator or motor, anything, no comparison. At some speed N we take. And if you take synchronous motor, what is the speed it rotates always? Only synchronous speed. Synchronous motor rotates at synchronous speed. First of all, what is the speed of synchronous motor means synchronous speed. Okay, but first of all, is the motor is self-start? No. Synchronous motor is not a self-start motor. It doesn't know where it has to rotate. Then how it is rotating at synchronous speed? Yes, we arranged something so that the motor is rotating at synchronous speed. What is that? Starting method. So mainly we have auxiliary motor starting or damper winding starting, like this. So we are arranging some arrangements such that the motor should be self-start. Actually, it is not self-start. We connected some auxiliary motor and we have overcome that inertia of the rotor. Then magnetic locking takes place. Then only it rotates at synchronous speed. So like that, induction motor. If you talk about induction motor, what is the speed induction motor rotates always? At a speed n less than ns, less than synchronous speed. Induction motor always rotates at n less than ns. N less than ns. Okay. Now, is the speeds are all motors are different? Same? No. DC motor n, synchronous motor synchronous speed, induction motor less than synchronous speed. So no motor is rotating. All motors will never rotate at one constant speed. Now, based on the speed of the motor, we will have applications. Induction motor, some application. Synchronous motor, some application. DC motor, some applications. Now, tell one important difference in these three motors. One important point. This is one important speeds, different speeds. And another important is this is regarding starting of motors. Which motors are self-start? Which motors are not self-start motors? Out of this, DC motor is self-start or not? Yes, DC motor is a self-start motor. Synchronous motor is a self-start motor or not? No, this is not a self-start motor. Next, induction motor, again two types. Single phase induction motor, three phase induction motor. Now what about single phase induction motor? Self-start or not? Single phase induction motor is self-start or not? No. Three phase induction motor? Yes. So there are some motors self-start, some motors are not self-start. Okay, at least some of you know about this. Okay, you know about this. Now my question is, how DC motor is self-start? Or tell first how three-phase induction motor is self-start. What is the reason behind three-phase induction motor is self-start? Tell me. Most of you know that point. Why three-phase induction motor? How three-phase induction motor is self-start? The reason is RMF. Yes, very good. Rotating magnetic field. Because of RMF, rotating magnetic field in three-phase induction motor, it is a self-start. That is okay. Single-phase induction motor is not self-start. What is the reason? Single-phase induction motor is not self-start. So I think this is also you know. What is that? Yes. In single-phase induction motor, we have two fields. One is forward field, another is backward field. If two fields are dragging a rotor in both directions with both torques, forward torque and backward torque, then in which direction rotor has to rotate? No direction. Suppose assume that uh, uh, both your friends are dragging you in both directions. Your friends are dragging you in both directions with equal force. Then in which direction you can move? No direction. You cannot move in any direction because both sides equal force are acting. That's why you cannot move in any direction. Same thing will happen in single phase induction motor. That's why rotor unable to rotate in any direction. Both sides having equal force or equal torque. That's why it is unable to rotate. Now DC motor, how it is self-start? Tell me that point if you know. How DC motor is self-start? You have to answer this because just now we completed single phase. Why it is? Now tell how DC motor we are saying it is a self-start. Tell me. No back EMF, not back EMF. Simply try to answer simply. Just now you said single phase induction motor, not self-start. Why? There are two forces. Yes, very good, very good. Unidirectional torque. DC motors is having unidirectional torque. Only one direction torque will produce, not two directions. If it is a single phase induction motor, two directions we have torque. That is unable to rotate. But DC motor will produce only one torque. That is called unidirectional torque. That's why DC motors are self-start. Now synchronous motor. Why it is not self-start? Tell me. Why it is unable to self-start? There is also RMF. However, there is RMF in three-phase induction motor. Here also we have RMF, but still it is unable to start. The reason is, yes, very good. The answer for this is inertia. Inertia, that is due to heavy body it is. Synchronous motors are generally large size, high power ratings. The rotor weight also very high. For that heavy rotor, even RMF is producing, the torque is not sufficient to drive the rotor at the time of starting, because generally to move a heavy body, what is the force required? Very high. Suppose you take a bus and car. Bus is like synchronous motor, car is like induction motor. Suppose there are four persons. The four persons are not sufficient to drive or to push the bus, but the same four persons can push the car easily. So like that, three-phase induction motors will be small size when compared to synchronous motors. That's why synchronous motors is having high inertia of rotor, because heavy body that is. That's why even there is RMF, the torque is not sufficient to drive the rotor. Because of that reason, it is not self-start. Okay. So like that, there are some important differences. Again, operating power factor, no need to tell. Now tell me one important point, that is, mm, out of this out of these motors, one motor, generally motor purpose is what? Mechanical application. Motor, mechanical purpose we use. But there is one motor for both mechanical purpose and electrical purpose. Which motor that is? Yes, you know that. One motor we use for both mechanical and electrical purpose. Which motor that is? One motor we use for both mechanical and electrical. Yes, very good. Synchronous motor. Synchronous motor is suitable for both mechanical and electrical applications, because synchronous motor we use as condenser, capacitor to improve power factor in power systems. This is the only motor, two applications, mechanical application plus electrical application. Remember this pointer. And remaining DC motor and induction motor only for mechanical purpose we use, no electrical purpose. Okay. So take a break for 20 minutes. After that, we see the principle of motor, and then we shift to directly simple loop generator. So take a break for 20 minutes. Right. Principle of motor. Next one, motor principle. What is motor principle? Simply, it is Lorentz force principle. Motor principle is nothing but Lorentz force principle. Lorentz force principle. What is the statement of this? Whenever a current carrying conductor is placed in a magnetic field, it will experience a force. Okay, so write the statement. Whenever a current carrying conductor is placed in a magnetic field, it will experience a force. Okay, the statement of this. Now, simply consider a current carrying conductor in a field. Assume that north and south poles. Field is there between north to south. Place a conductor here. Current carrying conductor, not only conductor. Only conductor is for generator. Now place a current carrying conductor in this, carrying a current I. Now in between already north to south there is a flux. Let it is phi 1, main flux. Now due to current carrying conductor around that, so according to right hand thumb rule or grip rule, if current is thumb indicates current direction, then the 4 fingers around the conductor will indicate flux direction. Now around this there is a flux. Let it is phi 2. Now there are 2 fields or not? Yes. Now due to this there is a force experienced on this. Whenever a current carrying conductor is placed in a magnetic field, it will experience a force. Now a force will produce in this. Now how to find the direction of force? Now tell me here first one question. A current carrying conductor is placed in a magnetic field. It will experience a force. Now due to that force, the conductor will rotate or not. Tell me. Now this conductor will rotate or not? Tell me that. It will rotate or not? Due to this, the conductor will rotate or not? No. It won't rotate. Answer is no. So I'm saying whenever a current carrying conductor is placed in a magnetic field, it will experience a force. Now due to that, conductor will rotate or not? No, conductor will not rotate. If conductor is rotating, no, there is a magic here. Conductor will not rotate. Conductor will not rotate. What is the reason for this? Observe. We are saying that force is produced. Now what a force will do? Force will make an object to move linearly or to rotate rotationally. Force will make a body to move linearly. So conductor will move here. Force is acting on that. So due to that force, it will move in one direction. Maybe this direction or this direction, but not rotation. You don't get rotation here. Conductor will not rotate here. If you want rotation of the same conductor, now the figure is like this. Same current carrying conductor, you should not place directly in between the field. Let us see like this. Consider it is a rotor. Now in that rotor we have number of slots. Now in that one of the slot I will place a current carrying conductor. One current carrying conductor I placed in the slot. Now this conductor will rotate or not? Yes. Now it will rotate. See, in the first figure there is a force, but in second figure there is a torque. Second figure we have torque. Now due to that torque, now this conductor will rotate. Conductor rotating means rotor also rotates. Now rotor is free to rotate in any one direction, clockwise or anti-clockwise. Now tell me what is the direction of force or torque? Now who will give the direction of force or torque? Fleming's left hand rule. Now in order to find the direction of motor, we need to apply Fleming's left hand rule. Previously right hand rule we applied for generator, that is to find in which direction EMF induced or current is flowing. But now for motors, to find the direction of motor, you need to apply Fleming's left hand rule. Okay, so write that statement here. The direction of force or torque, the direction of force or torque can be found by Fleming's left hand rule. Now I will show you here the two rules are same or not. Fleming's left hand rule. The direction of force or torque can be found by Fleming's left hand rule. Let's see that. Right, heading Fleming's left hand rule. Fleming's left hand rule. See, both rules are same. Right hand rule, left hand rule, both are same. If you remember any one, enough. Both you have. Fleming's left hand rule. See the statement of this. Same as right hand. Keep the three fingers. Index finger, middle finger, thumb finger mutually perpendicular. Then if the forefinger indicates direction of flux, forefinger indicates direction of flux, and middle finger indicates direction of current in the conductor, then thumb indicates direction of force or torque. Now right hand also same or not? Check one time. What is the forefinger of right hand? Flux. Okay, here also flux. Left hand also flux. Now what is the Fleming's right hand case? The thumb indicates what? Motion of conductor. Now what is the thumb in case of left hand? Direction of force or torque. This force or torque nothing but motion only, no? Yes, motion. What is the middle finger in right hand? Middle finger in right hand. Current direction or EMF direction. Now what is the middle finger in left hand? Direction of current. Both are same. Both rule statements are same. Only right and left. That is only different here. Remaining three finger statements, whatever is there in right hand, left hand also same. In right hand, thumb we call motion of conductor. The same thumb in case of left hand we call force or torque of the conductor. Force or torque produced. That is only motion here. Rotation. In which direction conductor rotates. Okay. Now write the statement once. If forefinger or index finger indicates direction of flux and middle finger, because we are placing a current carrying conductor. Now middle finger indicates direction of current in the conductor. Direction of current. Then the thumb finger indicates direction of force or torque. Direction of force or torque. Okay, so both rule statements are same. Don't confuse like it is different. Don't remember like that. Both are same. If you learn any one, enough. Now observe in the second diagram, what is the torque direction? Tell me. Apply your forefinger, left hand rule there. North to south flux direction. North to south flux direction. So forefinger keep along the direction of flux. Keep the forefinger along the direction of flux like this. Okay. Now here current is cross. Middle finger. What is the middle finger indicates? Current direction. So cross na it is. Cross means it should go inside the ball. Then you should rotate the finger or hand like this. Middle finger should go inside. Forefinger should be in this direction. Now observe your thumb finger. Your thumb finger I am getting in the downward direction. Therefore, that force or torque produced in downward direction. Then in which direction rotor is twisted? The rotor is twisted in the anti-clockwise direction. So it rotates in anti-clockwise direction. Okay, so this is the direction of torque we have to find like this. Got it all of you? Faraday's law will say only EMF induced. Lorentz is what? Force. That is different. This is different. Okay. Why in first case it is not rotating? Because in first case, observe in the first diagram, here just you are placing a conductor in the field. There is no rotational system here. You are placing a conductor in the field. Now a force is produced. Now what? Because of the force, a body will move linearly, but not rotationally. No, rotationally that itself cannot move. If you want a rotational direction, then you should put the same conductor in a rotational system. It is linear system. Okay, force and torque. Clear now? It cannot rotate in first direction. First figure. Okay. Next, I will give one more figure. Try to answer that. One more question. Try to answer the direction of motor. Write the question. The direction of motor is dash. The direction of motor is dash. So this is the figure. What is the direction of motor? Tell me. Direction of motor is dash. Clockwise or anti-clockwise? Yes, right. Mm. Yes, answer is right. Clockwise is correct. Yes, answer is clockwise because observe north to south flux direction. Okay, flux it is. And let us place your finger at this dot first. So forefinger flux direction in this direction, and current direction here dot means coming outside only, no? So with respect to me, it is coming outside. So my middle finger should be towards me, and my thumb is coming upward direction. So the torque produced is in upward direction. Force or torque upward. Now at here cross it is. What is the direction of torque here? So if you place again finger, current direction is cross going inside. Now let us move the hand exactly downwards because middle finger should go inside the board and forefinger is towards this. Now my thumb finger is I'm getting in the downward direction. So torque is in downward. Then overall twisting is in clockwise direction. So motor will rotate now in clockwise direction like this. Okay. So direction of motor is clockwise. So if it is in actual offline case, we can show better because our hands and fingers is exactly visible. But here it is little difficult because directly I cannot apply on board here the fingers. That's why I'm showing directly. So try to understand. Okay. Simple. Which rule means agar suppose it is motor. For motor, torque direction required. So for motor, we always apply left hand rule. And for generator, to find the direction of current or EMF, we apply right hand rule. Okay. Next, one more question. Try to answer this. The direction of motor in this figure is dash. See this? Now tell me what is the direction of motor in this second question? Clockwise or anti-clockwise? Is it clockwise or anti-clockwise? Okay, right. See now, answer is clockwise is correct, because now I given two conductors I placed in two slots with current different magnitude. One is 5 ampere, another is 7 ampere, both going in same direction. So like that I arranged. Now, what is the torque direction first? See, north to south flux direction. So mark the flux direction first. Now let us find the torque direction by applying Fleming's left hand rule. Okay. Now here middle finger going inside the board. Forefinger is same direction flux. Thumb finger is coming downward direction. So torque is in downward direction. And here also downward direction only you will get torque. This is making the rotor to rotate clockwise, and it is making the rotor to rotate anti-clockwise, opposite directions. But which torque is greater? Let it is T1, it is T2. What is the relation between torques? T2 is greater than T1 because it is proportional to magnitude of current. More current, more torque. Less current, less torque. That's why as T2 is greater than T1, T2 means clockwise it is. T1 is anti-clockwise. That's why finally rotor will rotate slowly in the clockwise direction only. Resultant torque is in clockwise direction. So rotor continue to rotate in clockwise only. Okay. So whenever same currents are given, you have to check magnitude of currents then. Next one, right hand thumb or grip rule. Right hand thumb or grip rule. So I think almost everyone knows this, but those who recently the last batch joined, so take it is right hand thumb rule or grip rule. So if the right hand thumb indicates current direction, the four fingers around the conductor indicates flux direction, and vice versa it is. So write directly, if the right hand thumb indicates direction of current, then the curl fingers indicates direction of flux, and vice versa. So here we have two cases, like if there is a current carrying conductor carrying a current I, then around that conductor there is a flux. What is the flux direction? Suppose hold the current carrying conductor in your grip. So actually we cannot hold current carrying conductor, just assume current carrying conductor is in the grip inside, and thumb indicates current is coming upward direction in the conductor. Then the four fingers, however, they are curling in the same direction, flux also rotates around the conductor. Assume that here flux is going, my four fingers going inside here and coming outside here, dot, going inside, coming outside, flux is rotating around this. This is one case, and another case is electromagnet. If it is like a coil, let us allow a current is moving in this direction. Now however current is moving, current is curling in the same direction, curl your four fingers in whatever the direction current is flowing, in the same direction put your four fingers, then thumb indicates flux direction. So this is the flux direction. Okay, this is our flux. Vice versa it is. If thumb indicates current, four fingers is flux. If four fingers indicates current, thumb indicates flux. Vice versa. Okay. So this is maximum enough to understand rotating machines. The basics to understand rotating machines, mainly Fleming's left hand rule, Fleming's right hand rule, right hand thumb rule, and Faraday's law. Anyhow, we know that very well. Okay. Now let's see the next simple loop generator concept. Simple loop generator. So if you understand well this one, how we are getting DC voltage from DC generators, you can understand easily from that. Okay, simple loop generator, if you have understand well, why we call it a simple loop, why we call simple loop generator. So whether it is DC generator or synchronous generator, you should understand simple loop generator well first. Then the next concepts will be very easy. Okay, now here we have two cases. Case 1 is commutator case, case 2 is slip ring case. Okay, first we will see commutator, then in second case I will replace commutator with slip ring. There I will show you how you are getting AC there, and with little clarity figures, because actual simple loop whatever the diagrams are there, they are completely wrong. So wrong in the sense the looking, the way the figures looks is wrong. Now I will show you the side picture of the actual machine, how it is connected and all commutators. Here, observe this. Observe. First I am taking simple loop generator case 1 with commutator case. Simple loop generator with commutator. So this is also called split ring. Commutator is also called as split ring. After that we have slip ring. Split ring is different, slip ring is different. So both are not same. This is also called split rings. Split ring. So I will show you here why we call split ring it is. Ring is splitted. Assume that there is one ring, and that ring we will split into two parts. That's why we call split ring it is. Nothing but commutator only. Okay, take the figure. Take the figure simultaneously. So take the figures. So actually the figure whatever is looking, actually that is wrong indication. whatever the figure we are drawing, that is two-dimensional. Actually, you have to imagine that loop is not vertically down. The loop is vertically towards you. Towards you. Means if it is north and south, loop is rotating like this. Assume that north pole, south pole it is. Now loop is like this and it is rotating in this way, clockwise or anti-clockwise. But how it is looking? It looking like vertically downwards. So actually that is wrong indication. But two-dimensional only we can draw, no? That's why that problem. Now I will show you actual figure how it is. Observe now. Just complete the figures. Pulakit. In the magnet second case, it is in the right hand thumb rule. So what it is if the four fingers. So in the right hand thumb rule, four fingers means this four. This is thumb. If the four finger indicates current, thumb will be flux, or if thumb indicates current, four fingers will be flux. Okay. Now in second case, I am considering the four fingers. So let us curl your fingers. So how current is flowing? Plus to minus, like this. Like this current is circulating throughout the coil in this way. Now, however current is flowing, in the same way I curl my fingers, four fingers, then thumb is coming in this direction. That's why flux is in this direction. Okay. So anybody still wasting time in the YouTubes? So in the previous classes also I said that. So these 3 months are so much crucial. These 3 months are so much crucial. The whatever you prepared in these 3 months, that is only with you in the examination. So whenever time is coming nearby, it is whenever it is approaching towards examination, and nearby that days only important, because whatever you prepared during that is only will be remembered in the examination. Okay, so don't deviate now. Concentrate these 3 months like anything. Those who are sincerely preparing for GATE or engineering services, so concentrate these 3 months. Very, very crucial. So an advantage is prelims also now little 1 month later, January. Generally it is January month only they conduct, but now it is chances there. So utilize that. Try to get good ranks. Try to settle as much as possible earlier. Now observe this. Now I will draw the same figures how actually in machine they present. Actually, suppose there is a generator directly, DC generator. How, why we call split ring is, observe here. This is a ring. Commutator looks like a ring it is, and this ring we are splitting into two parts. And this is only commutator here. This is commutator. And the two segments X and Y, commutator segment we call X and Y, and the two segments are isolated by mica insulation it is. Both are separated, splitted. That's why we call split ring it is. And why we call simple loop it is first. Loop means closed path. So to provide that loop, we are having a resistive load. A resistive load is taken. Otherwise, loop will not form. Closed path will come only when you connect some load. For that, a resistive load is taken. Okay. Now observe. Why we call simple loop is this loop will have only 1 turn. This loop is having only 1 turn, and it is having a closed path through resistive load. So a loop is formed. Current can flow in this now. So how that current will flow and all, we will apply now right hand rule From there we will decide. Okay, simple loop generator having single turn connected to a resistive load through commutator and brushes. Brushes are fixed always. Brushes will never move. B1, B2. B1, B2 brushes will never rotate. Now I will show the actual machine diagram. Observe here. So all these figures you should remember so that easily you can understand this. Observe. So actually it is rotor side view I'm drawing, rotor side view, and here you have poles, north pole, south pole. There is poles here, north pole, south pole. Actually this is the correct one. This is the correct one, but that figure is looking wrong. See, loop is here. Conductor AB in one slot, CD is in another slot, and this is called overhang or end connection it is. So whatever this upper part is there, BC we call end connection. Also called overhang it is. Also called overhang. If you see actual machine, it will be like this. This is overhang. Okay, let it is AB, AB, and it is C, D. And on the same shaft, we have commutator also placed. On the same shaft, commutator also will be there. Same shaft, commutator also connected. Now the ends of the loop connected to commutator segments like this. And on the commutator, we have brushes. On the commutator, there are brushes. And here we are connecting resistive load. This is the exact figure. Okay, now clear all of you. What is the figure? This is exact one. But how it looks? How it looks? It is completely wrong indication. No? You cannot understand from this figure. You cannot understand because to apply the Fleming's right hand rule, we have to rotate either in clockwise or anti-clockwise. But here there is no rotation like that. It is rotating like this or like this. How it is possible? This is the exact figure. Now got it all of you? What is the exact actual figure it is? Here we have M, L, let terminals. Okay, this is side view of the machine. Now same figure, front view I am drawing. Front view. See that front view, only front view. Let north pole, south pole. Here there is conductor AB. Let AB it is, CD it is. AB in one slot, CD is in another slot. CD. Assume that I am rotating clockwise direction. Okay. Now tell me in conductor AB in this position, what is the direction of current? In conductor AB, direction of current is dash. Flux direction north to south. Forefinger indicates flux direction north to south. Now when you rotate clockwise, see clockwise indication I given prime mover. Then AB will move upward direction, CD will move downward direction according to rotation. Now based on the rotation, what will be the direction of current? Apply the forefinger, your Fleming's right hand rule apply. Forefinger flux direction, motion is in upward direction. Now middle finger is going inside the board. Inside means cross, and here dot. Now conductor AB current is cross, CD current is dot. Clear? Now let us assume rotor is half rotated. When you rotate the rotor by half, now AB will go under south pole. Poles are fixed. Poles will never rotate. Stationary, no, that is. But here AB will go under south pole. CD will be under north pole. After half rotation. After half rotation. Now tell me in CD what is the current? In this position in CD what is the current? Cross only, no, it is cross. In CD the direction of current is cross. In AB current direction is dot. Okay. CD current is cross, AB current is dot. Now again rotate the rotor by half. Again you will get this position. Now what is the current in AB at that time? Cross. What is the current in CD? Dot. Now observe carefully these two figures. In one half rotation, current in AB is cross. CD is dot. In the next half rotation, current in AB is dot, changed cross to dot, and CD current is cross. So current in conductors changing. Positive, negative, cross means assume positive, dot means negative. Positive, negative, positive, negative means what is the nature of EMF? Sinusoidal, alternating only, no? Yes. EMF induced in every conductor is alternating only. Cross dot, cross dot, cross dot, continuously it is changing. But under North Pole, what is the current always? Cross only. See, whether it is conductor AB or conductor CD, anything that is under North Pole, what is the current here? Cross for clockwise direction. Under South Pole, what is the direction of current? Dot. So whatever the conductor under north, direction of current remains same. Now same points I will apply in the simple loop generator. Okay, observe, rotor is rotating like this. When rotor is rotating, commutator also rotates, but brushes will not rotate. They are stationary. Commutator only rotating, but brushes are stationary on that. So through the brushes, we will take the load or current outside to the loads. So see how we connect, how the load is getting current. Observe the figures. See, current under North Pole is cross, under South Pole is dot. Under North Pole is cross, under South Pole is dot. So same I applied here. Now let us mark here. North means going inside. Let it is going inside, and it will come outside here. Dot. Now C to D current is coming, and it is contact with segment Y. So through the segment Y, current will come outside. Through the segment Y, current is coming outside, and current is flowing M to L through the load and enters at B1, and this is the closed path. So current is flowing like this. Okay, in the first half rotation, so you have to start at the same time. I will draw this waveforms of EMF and also output. Let it is 90 degrees, 0 degree, 90 degree, 180 degrees, 270, 360. Okay, now let us consider 0 degree position means like this. North Pole, South Pole. Assume that 0 degree means AB here, CD here. So I cannot show with any paper and all here. That's why I'm showing in a figure itself. Observe. Assume ABCD in this position. North and South here. AB in one slot, CD is in another slot. So in this position, is there any EMF in the conductors or coil or loop at that time? No EMF, because what is the motion of conductor? If you rotate clockwise, what is the motion? In this direction, motion in this direction. So they are moving parallelly with flux lines. So no flux cut by the conductors, no EMF. That's why this is 0 degree position. It is a 0 degree position. In this 0 degree position, EMF induced is 0. 0 EMF. Now let us rotate this rotor from 0 to 90 degrees. So when you rotate 90, AB will come here, CD will be here. Okay, AB will be here, CD will be here after 90 degrees. Now whenever you are rotating, slowly EMF flux cutting increases or not? Yes, it will cut the flux line, cuts the flux line, cuts the flux line, and maximum EMF always will come exactly along the polar axis or D axis. The maximum EMF induced along the polar axis or D axis, and minimum EMF along Q axis. Minimum means 0 EMF here. This is Q axis or MNA, magnetic neutral axis. So when we rotate from 0 to 90, EMF increase, maximum at 90 degrees. And again, if you rotate one more 90 degrees, EMF again decrease. At 180 degrees, EMF will be 0. So 0 to 180 degrees, EMF will be like this. Now observe what is the direction of current here. A to B. 0 to 180 degrees, current is flowing A to B, C to D, and across the load M to L, current is going M to L. Now I will mark that is here. Current direction A to B, C to D in the first half rotation. And the direction of current across the load, output or load, is M to L. Same variation because voltage current in phase for resistive loads. That's why let current direction is M to L. Okay. So one half rotation over. When we rotate 0 to 180 degrees, like this EMF induced in conductor, and in the same way current also coming to load M to L. Now let us see what happened after half rotation. See that after half rotation, conductors will interchange or not? Yes, definitely they will interchange. Now CD will come under North Pole, AB will come under South Pole. Then what is the current under North Pole? Cross. So going inside. Current direction is going inside and coming outside. Now check. Whenever loop is rotated, commutator also rotates simultaneously. Both are same shaft now. That's why commutator also rotate at the same time. Because of that reason, segments also interchange. Observe here. When AB comes to South Pole, X will come under South Pole. This is. Segments also will interchange. Now B to A current is coming, and through segment X, current will come outside through the brush B2. This is the direction of current M to L, M to L. Now enters into brush B1 and then conductor DC. So this is the direction of current in the second half case. Now it will continue for next rotations, same as it is. Now what is the direction of current within the conductor? Previously C to D, now D to C after half rotation. That's why if C to D is positive, D to C will be negative. Because of that reason, now the direction of current in the loop is D to C, B to A. D to C, B to A. That's why I taken negativities. Previously A to B, but now B to A, reverse. So current is flowing like this. But what is the direction of current at load? Check it is. Previously M to L, now also M to L. No change of current direction at loads. Same direction current is coming. Even the current is changing inside the conductors, but no current change in the load. That is M to L only current is coming. M to L only current is coming. That means, what is the nature of EMF induced for one rotation? AC, alternating. The EMF induced for one rotation is AC. But what you are getting at the output or load, you are getting pulsating DC. DC, but not exact DC directly. Let us take pulsating DC, because pulsating it is DC only, but pulsating. Not like a straight line, it is. It is not having like this straight line, constant DC voltage. It is not like this. We are getting pulses. Okay. Now who is converting that AC into pulsating DC? Commutator. Commutator is converting the AC into DC. That's why the commutator is called as, what we call commutator? So don't say only rectifier, because it is rectifier, no doubt. AC converted into DC. But don't say only rectifier. There is a full name for this. That is, it is a mechanical full wave uncontrollable rectifier. This is completely you have to answer. Mechanical full wave uncontrollable rectifier. Okay. Mechanical. Why mechanical? Because we have another device which converts AC into DC. What is that? Rectifier. Actually, in power electronics, we learn using thyristors or IGBTs, we design rectifiers. So there, That is a static device. Thyristors, all semiconductor devices are what? Static. They don't rotate. Static only. Even they will convert AC into DC. So they are static. That's why in power electronics, if you remember, in every concept, rectifier, choppers, or voltage controllers, everywhere, inverters, everywhere, we write a static device which converts AC into DC or DC into AC or DC into DC, choppers. So that is called static. But what commutator here? Rotating or not? Yes. When armature is or rotor is rotating, commutator also rotates. Then only it is converted. Otherwise, it won't convert. If commutator is not rotating, it cannot convert. It will fail. That's why it is a mechanical full wave. Why full wave? Both negative half, positive half converting. No, it is full wave. Uncontrollable rectifier. That is important. Just like diodes, uncontrollable rectifier it is. Because if you see using thyristors, how the output voltage we get based on the firing angle. Suppose I given alpha firing angle here. From here I will get the output voltage. From here I will get the output voltage. So here you can control the output voltage by controlling alpha firing angle. That is a controllable. But commutator is what? Are you giving any firing angle to commutator to start there only? No. So that is uncontrollable device. That's why it is giving some signal. That's it. Whatever it will give, it will give. That's it. We cannot change again. That is uncontrollable rectifier. Okay. Now our task here is we don't want pulsating DC. DC means we need exact DC like this. This is we want. Then how to get a constant DC voltage from pulsating DC? This pulsating DC we need to convert into constant DC. How can we convert? Yes, using filters. One method by using filters. So using the filters, filter out AC present in the signal. Which signal will pulsate? AC only will pulsate. DC will never pulsate. Constant. So let us use filters and filter out the AC in that and then convert into pure DC. But using filters is costliest and that is not economical also. So that is difficult task. Then how can we make exact DC? Simple. Let us increase number of coils in armature. Increase number of coils. Whenever number of coils increases, automatically your output voltage will be DC. You no need to use any filters. Yes, no need to use any filters. Same thing is happening in DC generators. No need of any filters. Still you will get the constant DC voltage. That is by using more number of coils in armature. So I will show you with the graph also now how by increasing coils output voltage will become DC. Okay, first complete up to this. Write one point. Write one point here. The commutator converts. First write one point. The simple loop generator is having the simple loop generator is having singleton connected to a load through commutator and brushes. Through commutator and brushes. Okay. For one rotation of the loop, the nature of EMF induced is the nature of EMF induced is AC, which is converted into into pulsating DC, which is converted into pulsating DC by using commutator. Hence it is called as a mechanical full wave uncontrollable rectifier. Okay, now make a note and write the statement. The pulsating DC can be converted into, yes, by increasing number of poles, also correct. The pulsating DC can be converted into a pure DC. The pulsating DC can be converted into pure DC by increasing. The pulsating DC can be converted into pure DC by increasing number of coils in the armature. By increasing number of coils in the armature. By using number of coils in the armature. Okay, now we will consider one example. So if you observe simple loop nothing but you assume single turn coil, that is. Simple loop means single turn coil. One coil it is, or one turn, or assume that one coil. What is the difference between one turn voltage, one coil voltage? Turn voltage is let 1 volt. If there are 10 turns in a coil, what is the voltage? 10 volts. Magnitude only will change, but your shape of signal, everything same will be there. Assume that this is itself one coil. Now we will take two coils. Then we will check what is the output signal we are getting. Okay. Now right here, consider example. Write example. Consider an armature with two coils. Consider an armature with two coils as shown in figure. So I'm taking an armature with two coils now. Let us consider this is having two coils. North pole, south pole. So I am taking two coils in this. Let it is one coil, 1 dash, and it is 2 dash. Okay. So one coil has how many sides? Two sides. Coil means this is. So in the armature winding, you will see all this clearly. This is a coil. So one coil may have any number of turns. 2 turns, 3 turns, 10 turns, 1000 turns. This is a coil. Now one coil has how many sides? Two sides. Let it is coil 1. Coil side 1. This is 1 dash. So one coil has two sides. 1 dash. Similarly, second coil 2 dash. Third coil 3 dash, and so on. Now one side is placed in one slot. Another side is placed in another slot. Like that. Assume that there are 4 slots. So total 2 coils are placed. 2 coils. Okay, 2 coils are placed. Now, when we rotate the armature or rotor, at a time, EMF induced in both coils at a time. Now, I will draw the figure for this. See here. Let the EMF induced in each coil. EMF induced in each coil. For one rotation only, I am taking 0 degree, 90 degrees, 180 degrees, 270, 360. Only one rotation I am taking. Next, it is output of commutator. And finally, I will draw resultant signal here. Resultant. See it is. Now, when you rotate one rotation, EMF will induce in two coils at a time. Now, according to the figure, tell me, assume that whatever the figure it is showing in the diagram, this is itself a 0-degree position. This is 0-degree position. Now, let us start from here. Now, in this position, what is the EMF in coil 2? What is the EMF in coil 2 in this position? 0 or not? And what is EMF in coil 1 at the same time? Maximum. Because coil 1 is along polar axis or D axis and coil 2 is along Q axis. So because of that, what is EMF in coil 1? Maximum. What is EMF in coil 2? 0. Now that is I am indicating in the diagram. EMF in coil 2 is 0. EMF in coil 1 is maximum. Okay, at 0 degrees. Now let us rotate the rotor. When rotor is rotated, what is EMF in coil 1? Decrease. What is EMF in coil 2? Increases. Coil 2 EMF increase, coil 1 EMF decrease. Now if I proceed, coil 2 EMF increase, coil 1 EMF decrease. 90 degrees rotated. Now if you rotate continuously like that, you will get EMF for one cycle or one rotation. This is the EMF induced. Okay, this is the signal 1 dash EMF in coil 1. This is the signal for 2 dash. So all of you clear this signal? At a time, 2 EMFs. Why? Because 2 coils. Suppose if you take 3 coils, so at a time how many signals you will get? 3 signals you will get. So all of you clear? Raise the hand up to this. Okay, right. So when we rotate at a time, EMF will induce in 2 coils. So that is I drawn here. If there are 3 coils, 3 signals you will get at a time. Now output of each coil. What is the commutator output? AC converted into pulsating DC. Now with respect to second coil, positive will be there as it is. Negative signal or negative half is converting into positive half. So second coil, negative half is converted into positive. This is for second coil, 2 dash. Coil 1, positive here. And this is coil 1, negative half, convert to positive by commutator. Commutator will convert negative half into positive half. And again it is positive. Okay, this is for 1 dash. So clear what is this signal? Second one is the commutator output of each coil. Commutator output of each coil. Okay, now resultant of the 2 coils, because across the brushes whatever you will get, that is not one coil voltage, that is number of coils voltage, that is resultant we have to take. So at the output, resultant, see here, concentrate here. From 0 to 90 degrees, what is the EMF of coil 2? This is coil 2, 0. But what is EMF in coil 1? Maximum. Now let us take average of these two. You will get some voltage, not 0. Now like that, 0 to 90, you will get the variation in this way. And 90 to 180 also same. 180 to 270 also same. 270 to 360 also same. Okay. Now this is your output voltage. This is our output voltage. Now what is the advantage of second 2 coil case compared to previous simple loop generator? In previous simple loop generator, this is the output voltage or current is becoming 0. It is becoming 0. That is AC is more. AC only will become 0. DC will never become 0. So it is having more AC content. But when there is 2 coils, the resultant is this. It is not becoming 0. Now let us increase number of coils are 10. If there are 10 coils in armature, then your output voltage is almost like DC or not? Your output voltage is almost like this. And if there are 20 coils, your output voltage almost DC. So by increasing number of coils in armature, your output voltage will become pure DC voltage. Okay, the output voltage will reach almost DC voltage. Take this figure. How commutator so how that resultant doing by commutator is commutator actually all coils internally connected in series, no, all the coils internally connected in series. So if in armature winding concept you will understand there how the coils are connected inside. There I will show you the complete armature winding picture, so there you will understand. But meanwhile remember this. Okay, so this is for one coil, this is for one coil output of commutator. When there are more than two coils, always the output voltage is resultant of the any number of coils. So that resultant we are adding here, that's it. Resultant we are adding based on the coil positions, resultant we take it. Okay, how commutator is converting negative half to positive half. Observe, that is I shown already here. Negative half is this, no, D to C, B to A, but in this negative half also across the load, what is the current you got? See, in the this is first half, A to B, C to D. What is the current at load? M to L. In second half also, what is the current in load? M to L only. Same direction current is going, nothing but internally EMF induced is what? Reverse. See, A to B, C to D. But after half rotation, D to C, B to A. It is reverse now within conductor. With respect to conductions, that is reverse. D to C it is going. But what is the direction of current at load? Same. So if you take it is reverse negative, but still under negative case also the current at load is same direction M to L. That's why we taken positivities. Negative is converted to positive. Okay, now frequency is there. Frequency also there for pulsating DC. See, suppose if you got a question here, how many pulses will be there in one rotation? Tell me, how many pulses we got here? This is one rotation, 360 degrees. In one rotation of the armature, how many pulses we have? 4. So how to find the number of pulses? The number of pulses per one rotation will be number of coil sides. The number of pulses will be number of coil sides. How many coil sides are there? 4 coil sides. 1, 2, 1 dash, 2 dash. 4 coil sides. That's why you will get 4 pulses here. Okay. So in one rotation, how many pulses? Or sometimes they will ask the questions. The number of pulses per half cycle is dash. Half cycle means 180 degrees. Number of pulses per half cycle. How many pulses are there in half cycle? 2. Nothing but if it is asked for half cycle, number of pulses equal to number of coils. So write that point here. Make a note beside this. Note. The number of pulses per half cycle. Number of pulses per half cycle equals to number of coils. Okay, number of coils. If there are 4 coils, how many pulses will be there in half cycle? 4 pulses will be there. For half cycle only we are calculating. That commutator segments and all in the construction I will show you clearly. Okay. Next. So is it clear? Now let us take case 2 here. First case is what? Simple loop generator with commutator case it is. Now let us take case 2, slip ring case. Right, case 2 with slip ring. With slip rings. Case 2. Simple loop generator with slip ring. With slip ring. Slip rings. Simple loop generator with slip rings. So observe here. Draw the figures again, same as it is, but at the end of the loop we have commutator here. But now at the end of the loop we have slip rings. Now I will show you the actual machine diagram also, how slip rings are connected here. First take the figures simultaneously. Take the figures. Mostly the class will be around 9 to 9:15 maximum. I don't take up to 9:30. 9:15 maximum. Okay. So we have to learn with interest, not like so much struggling while listening also. That much not required. Listen happily, but not with force. So same figure I am drawing with slip rings. That's it. So complete the two figures. Okay, so class I will take only up to 9 as you wish. Okay. So, okay. Because problem is not for you also. I am taking from 2 o'clock. Problem is for me also. From 2 to 5 I have to take, and again 5:30 to 9:30. 9:30 means it is also difficult for me. Okay, no problem. Whenever Sunday or when full day will come now, so there we will cover. 12 p.m. also you will sit. Okay, no problem. So no problem because from my side always I don't take so many days. I will plan accordingly to complete the total syllabus. So maximum 8 to 10 days we will complete this. Okay. Completed figures. Now I will give that machine diagram how we connect slip rings. Observe here. Slip rings how we connect. Actually, all these figures and all, if you see one time directly machine, no, suppose DC generator. If you see directly one time, you will get so much idea on that. That is practical learning is different, theoretical learning is different. So most of the people don't know where commutator, how brush assembly is placed, or where slip rings are placed, how it is connected. See, like this. I am showing the side view of the same rotor, side view. Same rotor, north and south pole. See how we connect the slip rings is AB in one slot, CD is in another slot. Now here we have commutator previously, but now no commutator. Slip ring. What is the slip ring size is shaft size. However, we wear ring to the fingers in the same size the slip rings also we design. Suppose if it is shaft, the same size of the ring we design, same size. And first let us place this end. It is A, B, C, D. One turn it is. Now let us place this end on the shaft, but directly not on the shaft. If it is the shaft, first you have to place some insulating material on that. So let us take some paper, surround that. Now on the paper, put the end of the wire. Now insert one ring from the starting, and the ring should be tightly connected such that ring is like this. Below that ring, there is a wire. Below that ring, there is a wire. Okay, this end is below the ring. Tightly connected on that. Tightly connected it is. Okay, this is one slip ring. Now another slip ring. Place the other end on the same shaft again by placing insulating material. Now take another ring and tightly connect. Below the ring there is a wire. Below the ring there is a wire. Now whenever rotor is rotating, no, the slip rings also rotate simultaneously. Now below the ring there is a wire contact. Now we will place brushes here. This is one brush. This is another brush. Now across these brushes, here we connect resistive load. Let it is M, L. resistive load it is. Now, whenever rotor is rotating, shaft also rotates. But over the slip ring, brush is continuously contact. Brushes will never rotate. Brushes are fixed. When rotor is rotating, slip rings also rotate here, but brush is contact on the slip rings. Now, across the brushes, we connected a resistive load. Current will flow. Now, observe what happened. Same figure it is. Two slip rings connected with each brush. Now, let us consider in first half rotation. What is the current under north pole always? Cross. South pole, dot. North pole cross, south pole, dot. Now, what is the current direction? Cross means going inside, dot means coming outside. Going inside, coming outside. Now, what is the direction of current at the load? Check now. See, C to D current is coming and the same current will come outside. As this is connected with this slip ring, through the slip ring current will come outside through the brush B2. This is the direction of current. M2L current is flowing. Now, same current will enter at brush B1 and then enters into the loop inside. This is the direction of current. Okay, A to B, C to D, and across the load M to L. Okay, I will draw it is in the waveform. A to B, same as it is, I will take commutator case 360 degrees 0, 90, 180, 270, 360. One rotation I take. Across the load, how the output you are getting, you need to check. This is EMF induced. What is the initial for one rotation? A to B, C to D. Let is it positive. Consider it is a positive. A to B current is flowing, C to D current is flowing in the loop. Assume that that is a positive. Now, what is the direction of current at load? M to L. Let it is positive. M to L. Okay. First half rotation over. First half rotation. Now, let us rotate the rotor by half. So, when half is rotated, CD will come under north pole, AB will go under south pole. Now, what is the current? D to C. Within conductor, reverse it is. D to C, then B to A. Now, check how current will come. See, this is the current direction. B to A, this slip ring is attached with brush B1. Now, through the slip ring, current will come outside here, B1. And then current is flowing into the load L to M and then enters here. Brush B2 through this brush and then slip ring. This is the direction of current. This is direction of current. So, loop is formed. Okay. Now, check in second case. After half rotation, within conductor reverse, D to C, B to A, reverse. At the same time, at load also current reverse. Previously, current is going in this direction, but now reverse. So, if it is positive, first case, now it is negative. So, current in load is reverse or not? Yes, reverse. Therefore, for the second half rotation, current at loop is reverse. Current in the loop is reverse. D to C, B to A. At the same time, current at the load also reverse. L to M it is now, not M to L. L to M, reverse. Here M to L. M to L. Now it is L to M, that's why I take a negative. So what is the EMF induced? AC for one rotation, alternating. What you are getting at load? AC only you are getting. So no conversion here. Now what is the purpose of slip ring? Just to collect. Otherwise, if there is no slip ring, can you collect that voltage or can you give supply to the resistive load, stationary resistive load? You cannot give. Assume that rotor is like this. Some people will get doubts here. Assume this is a rotor. Assume that no slip ring. No slip rings. Okay, no slip ring. AB is here, CD is here. Now directly I will connect to a resistive load. Is it possible to connect a resistive load directly without slip rings? Tell me. When rotor is rotating, your resistive load also will rotate or not? If rotor is rotating, your resistor also will rotate here. Not possible because generally loads are stationary. Loads should not rotate. If load rotate, it will damage. So in order to give supply to a stationary loads, we need a slip ring and brush assembly. We need a slip ring and brush assembly. Otherwise, we cannot supply. Okay. So what is the purpose of slip ring? Just to give supply to a stationary load. Slip ring will not convert anything like commutator case. So this is a AC generator. Now what is the previous case? DC generator. DC it is giving because of commutator. Clear? How commutator is converting AC into DC? Now one important observation here. So first, suppose I will give one point. Tell this. What is answer? That is in a generator. In a generator, if a brush is permanently connected, if a brush is permanently connected, if a brush is permanently connected with one conductor, then its output is dash. Its output is dash. Tell AC or DC. In a generator, if brush is permanently connected with one conductor, then its output is dash. AC or DC. Its output is yes. The output is AC. The output is AC. Yes, answer is AC it is. Because observe the figure now. Observe here. In first case, first figure and second figure, both cases, brush B1 is connected with which conductor? Check. See here, B1 connected with AB. Okay. Observe the second figure also. B1 connected with AB only. So one brush connected with one conductor permanently. But observe the previous case. This one. First figure, B1 is connected with AB. B1 is contact with AB. Second figure, same B1 is contact with CD. Now it is not permanently connected with any conductor. They are interchanging. So if a brush is permanently connected with one conductor, output is AC. Otherwise, if a brush is not connected, means output is what? DC. So remember these 2 points, important. If a brush permanently connected with one conductor, your output is AC. Because if it is permanently connected, no, if the conductor is under north pole, positive. If the same conductor goes at south, negative. That's why positive, negative, alternating will come. Otherwise, if you take commutator case, the brush is not connected with any conductor. They are changing continuously. So the output is DC voltage. Okay, so clear all of you. This is about a small simple loop concept. Simple loop generator. Clear all of you? Any doubts for today's class? Any doubt? So I will stop for today here. Tomorrow we continue. Tomorrow we start construction of DC machine.
Hello.
Hello. Naresh.
Sir,
Tell me.
Purpose of slip ring is to collect current. Then what is the purpose of brushes?
Without brush, slip ring, both required. Otherwise, if any one also not there, we cannot collect.
Okay, sir.
Okay.
Sir, 21F, sir.
Tell me.
Sir, here how you said number of pulse equal to number of coils, sir. But in resultant we get only 2 pulse, no, sir. But we have 4 coil sides, sir.
Number of pulses per half cycle means 180 degrees.
Okay, sir.
Then for 180 degrees, how many pulses you are getting finally? 2 pulses.
Oh, it's coil, not coil side.
If it is asked for one rotation, then it is a coil sides.
Okay, sir.
Okay.
Sir, and another doubt, sir.
Hello.
Sir, and another one doubt, sir. Here you
Oh.
said if number of coil is increased, it means we won't get the pulsate in DC, we will get a straight DC, sir.
Yes.
In power electronics, we say that is continuous current and with high inductance value, it will not reach to zero. Can we use that similar terms here, sir, with high inductance value?
No, because inductance we never talk in DC first.
Okay, sir.
That is not suitable.
So here resultant means we are adding the EMF of two coils.
Yes.
Okay, sir. Thank you, sir. That's it.
Sir, in slide number 23,
20.
3, sir.
Oh.
Sir, the CD conductor is there, no, sir. Rotating, it will get in contact with that brushes, no, sir. How it, in practical condition, how it will be, sir?
CD is not contact with brush. No, it is contact with slip ring. Slip ring is contact with brush.
Yes, sir. While rotating, sir.
While rotating also, under this end, this wire is always contact with slip ring. Okay.
It will be in contact with, it will be near to the shaft, sir.
Yes.
Okay, sir.
Next.
Sir,
Tell me, Avinash.
sir, the last topic you have told that if the brush is permanently connected to the one conductor, then the output is AC. Sir, will you please explain it once how it is?
So observe the figure here. This is
Yes,
slip ring case only, no? Here brush B1 is connected with AB conductor.
Yes, sir.
In the second figure also, same brush B1 connected with AB only.
Yes, sir.
So one brush is permanently connected with one conductor, no? Here.
Yes, sir. One brush
That's why what is the output you are getting? AC.
AC output.
Now observe the commutator case. First figure B1 connected with AB.
Yes, sir.
Second figure same B1 connected with CD.
Yes, sir.
That is changing, no?
Yes, sir.
That's why here brush is not connected with any conductor, but here it is connected with one conductor permanently. Then only we get output is AC.
Okay, sir.
Okay.
And sir, in the previous case, we have got output pulsating DC. Hello.
Yes. Commutator case, no?
Yes, sir. Okay. Thank you, sir.
Okay. Next. Next, anybody? Jyotika, raise the hand. I will unmute. So those who have doubt, raise the hand.
Hello, sir.
Hello, tell me.
Sir, why we have taken the cross at under North Pole, sir?
What is doubt?
Sir, why we have taken the direction of current cross under North Pole?
Because apply the Fleming's right hand rule here. Apply Fleming's right hand rule. Motion is upward direction. Under North Pole always motion upward direction. Now apply there, forefinger flux direction, middle finger going inside the board. Inside means cross only, no? Always under North Pole cross only. Okay. Dheeraj. Yes, winding should kept on rotor, because if winding is stationary, no, you don't get DC. You don't get DC. That's why in DC generators, armature winding must always place in rotor only. Then only commutator converts AC to DC. Okay. Clear? Slide number 9. What is that? What is problem doubt here? So in this figure, actually they given field is rotating in clockwise direction. Field direction they indicated. But according to Fleming's right hand rule, the thumb indicates motion of conductor. But they said that armature is stationary. Then we cannot apply directly. That's why what we take an assumption, considering the motion of conductor opposite to field. Then opposite means field is rotating clockwise. Now we take an anti-clockwise. Now if you rotate anti-clockwise, C1 will move upward direction. C1 dash will move downward direction. Now apply your Fleming's right hand rule. Forefinger flux direction, motion upward direction, middle finger outside the board. That's why it is dot. Okay.
Hello, sir. Good evening, sir.
Tell Shiva.
Sir, with commutator case.
Common?
Like with commutator case, like with split ring.
What is doubt?
Sir, here if we don't use split rings too, we can get the same direction of DC now. Then why we need to use commutator?
If you don't use commutator, how you will get same direction?
No, like anyway, if you consider the second diagram, the current is in the upward direction, and for AB conductors, it is downward direction. So anyway, if we connect in the circuit, it will be like from M to L only.
No. So in the same slip ring, you observe the slip ring case. Are you getting there? Same? No.
Yes,
So
sir. But
without commutator means only thing is slip ring.
Slipping, yes, yes.
Then how can you collect outside?
Okay.
Okay. So when there is commutator, then only output is DC.
Okay, sir.
Okay. Same direction will come current to the loads.
Yes, sir. Sir, and then in 8F. Sir, here at 2 and 4 conductors, we don't have any EMF. So it is because of that EMF equation, E is equal to BLV sin theta.
Like that also you can consider dynamic EMF, no? BLV sin theta. Theta is 0.
0 and sir, if we draw a coil, then I can't able to visualize like how it is not cut.
Coil?
When we
observe here, at this time it is moving parallel to flux line. No? When we rotate this position of conductor is moving parallelly with flux line, then it won't cut any flux here.
Sir, but 2 and 4 joins like a coil, and it is cutting the flux lines, no, sir?
No, that is coil sides only. No, coil side it is. See, this is one coil. This is one coil. Assume that this is side 2, this is side 4. This is in one slot. This is in another slot.
Another slot, yes.
Then at that time, the motion of the two sides will be parallel to flux line, or there is another definition like flux linkages. So whenever coil position is 2, 4, what is the flux linkages? Maximum.
Yes, sir.
Means flux lines all passing through the coil, inside the coil. If flux linkages are maximum, what is the rate of change of the flux linkages? D psi by dt minimum. Means minimum. 0 only, no?
Okay.
Like so that another definition.
So when 2 and 4 conductors, when it reaches to 1 and 3 position, the EMF
then it is maximum at that time.
Yeah, okay, sir. So we can say that the rate of change of flux is like maximum at 1 and 3 position.
Yes.
Okay, sir. So and then last out is 15F. No, sir, you gave one question like that 5A and 7 amps. Yes, sir, this one. And here the direction of current is same in both conductors.
Same so only, but magnitude of current I given different, 5 ampere, 7 ampere.
Yes, sir. What I'm asking is it possible in practical cases?
No, generally we don't use. No, unnecessarily. Why we reduce the torque? Tell me.
Okay.
If we place like that, the torque production is less. Suppose you remove 5 here, then how much torque will come in one direction? Very high torque. That is advantage. Generally, we don't give practically like this. Okay.
Okay, sir. That's it.
Okay.
Thank you, sir.
Sir.
Tell me.
Sir, in the same slide, that 14F.
In the first question, sir, in north side pole you wrote that dot, sir, but normally it should come cross, no, sir. Is it correct or is some?
This is motor. That is our wish. Anywhere you can supply current. Motor, no, it is.
Acha, okay.
Under north pole cross means that is not permanent, because if you rotate the rotor anti-clockwise, no generator, then current direction will change. Now, why we taken cross under north pole? Because we are rotating clockwise. According to motion, under north pole always cross only we get. Suppose if you rotate anti-clockwise, now under north pole, what is the current direction? Tell me. Is it cross? No. Now it is dot, and south will be cross. Apply Fleming's right hand rule now. Anti-clockwise direction I'm taking.
Okay.
Now what is the south? Upward, north, downward, motion.
Downward.
Now north to south, and motion is upward. Now at south I will get cross. Okay.
Okay.
Current direction we have to find at that time, not fixed it is. Okay.
Got it, sir. Thank you, sir.
Okay.
Hello, sir.
Tell.
Sir, could you please explain me the term why we use the split ring in the simple loop, sir?
Page number?
Sir, I'm not sure. Simple loop of generator with commutator, sir.
Commutator.
Yeah, why we have used the term split ring, sir?
Because it is commutator is like a ring only, ring, but it is splitted into two parts, no? Exactly, by mica, and this is mica insulation. Insulation it is. The two parts are fixed. It is made into two halves exactly.
Okay,
That's why
sir.
we call it is like a split ring. Ring is
Yeah, okay.
splitted.
Sir, will this concept of a simple loop generator will be similar to that of motor?
Motor means in place of resistor here, give supply.
Yeah, okay, sir.
Then it is
Thank
motor.
you, sir.
Okay. So I'm closing for today. Tomorrow we meet.
Hello, sir.
Sir, on the
Tell.
last one.
Tell me.
Sir, in this with commutator, that commutator is fixed with the shaft, no, sir?
Yes.
That commutator and the slip ring both are fixed
That is
with
the
shaft.
second, this figure, no? That's the given.
Both are fixed with shaft.
Fixed.
Okay. Sir, if the machine which we don't know whatever that machine, if we say differentiate between AC machine and DC machine, how we can differentiate, sir, without knowing that supplies and other things by looking?
Looking means we have to identify commutator is there or not. Commutator.
Is it?
If there is no commutator in that, that is a AC machine. If there is a commutator, that is DC machine.
Okay. Means from outside we can say that see that
Outside
commutator,
we
sir.
cannot say. Outside we cannot say because commutator should be inside the rotor, inside the stator.
Yes, sir. That's why I'm asking.
Directly we cannot say that.
Is means in our house we are using induction machine, no, sir. We means DC machine we can't use rarely, but if we ask any interior as that, how we differentiate without seeing that commutator and other things supplies, and how can we differentiate AC machine and DC machine? What can we answer, sir?
Then directly by looking at the outside structure we cannot say, because every machine's shape in design is same, no, almost. Then outside looking means how can we say directly? That is not possible.
Okay, sir.
Okay, there is some universal motor, single phase AC series motor, universal motor, and induction motor, both almost same. Then we cannot differentiate directly by outside looking. So we have to see the rotor construction once. From there only we can decide what type of machine it is. Otherwise, only stator structure we cannot say.
Okay, sir. Thank you so much.
Sir, one last doubt, sir.
Tell me.
Sir, along direct axis, flux linkage will be maximum, sir.
Flux linkage is minimum.
Along Q axis it will be maximum, sir.
Yes, maximum.
At that, sir, but in direct axis EMF will be 0.
Yes, 0.
Okay, sir.
Direct axis EMF is maximum. Q axis EMF is 0.
Okay, sir.
See, when flux linkages are maximum, EMF will be 0.
Okay, sir.
Okay. If it is minimum, EMF will be maximum.
Okay, sir.
Okay. So better than all this, remember flux cutting or not. That's it. If it is cutting the flux, EMF will be there. If there is no cutting, no EMF.
Okay, sir.
Okay.
Thank you, sir.
Good night.